Welcome back to my course Aspects of Biochemical Engineering. Now, in the last lecture, I was discussing about the activated sludge process, how activated sludge process basically it is a CSTR with cell mass recycling. Now, activated sludge process is mostly used for the wastewater treatment process, and I described in the last class that that industrial more than 70% of wastewater treatment process that is controlled by the biological means. And there is a survey made by Central Pollution Control Board in India, and they observed that mostly the chemical and biochemical industry that we have in India that pose the water pollution problem. So, that now if you look at the chemical and biochemical industry, the wastewater mostly contain the organic material, the soluble organic material, and this soluble organic material when we discharge in the water courses, the whatever bacteria is there, they will grow and multiply and contaminated the water. And not only that, they secrete different metabolites that causes some toxic effect in the water. So, to safeguard this process, we shall have to do the wastewater treatment process, and most of the chemical and biochemical industry, they adopt this activated sludge process. Now, if you look at why this biological process mostly used for wastewater treatment process, the reason is that if you want to oxidize chemically, we shall have to use the potassium dichromate, potassium permanganate, and you have to boil with some time, so that whatever organic inorganic material is there, that will be totally oxidized. But when you do so, that wastewater also in other way increases the heavy metal contamination. As for example, if you treat with potassium dichromate solution, the chromium concentration of the water that increases. If you treat with potassium permanganate, the manganese ion concentration in the water that increases. So, heavy metal ion contamination, this is another problem that we will be facing. So, to safeguard this situation, biological process has some kind of alternative. The reason is that your bacteria can utilize the soluble organics very easily and convert it into the cell mass. And I try to discuss with respect to carbon balance. If you do the carbon balance of the system, we find that 50% of the carbon usually goes for the cell mass formation and 50% to carbon dioxide. Now, carbon dioxide that will go into air, but whatever that cell mass, 50% of carbon converted into cell mass, and which is insoluble mass, and we can easily separate it out. So, we can separate out easily. And I try to discuss that one key organism that is mostly used for the activated sludge process is Jouglia remigera, because they secrete the polysaccharide gel, and we know that the size of the bacterial cells is very small. It is 0.5 to 2 microns, and since the size is very small, it is very difficult to separate out, because and since this Jouglia remigera has the characteristics of secreting the polysaccharide gel, they have the agglomeration property. The particle, they will bind with each other and form the floc, that is the bigger particle. When it forms the bigger particle, they will precipitate it out. And so that activated sludge process is basically, as I told you, it is basically CSTR with cell mass recycling. And if you look at in this process, because I tried to discuss previously also, the major drawback of the chemostat process or CSTR process is the cell mass wasting from the reactor. And if your rate of cell mass that is going out of the reactor is more as compared to the cell mass growing in the reactor, so a time will come there should be no cell present in the reactor. If there is no cell present in the reactor, so we will not get any kind of reaction. To to avoid this kind of situation, what we can do, the whatever excess amount of cell mass that is going out of the reactor, we can recycle back to the system. So, the cell mass concentration in the reactor will be uniform and rate of reaction will be constant. So, our process we can operate very easily. So, this is the activated sludge process I try to discuss, and we develop kind of equation through which we can find out the cell mass concentration in the activated sludge process, also the volume of the reactor, how you can calculate. Now, when you do the recycling of the cells, I told you the main purpose is to increase the mean cell residence time. In case of chemostat process, the mean cell residence time is equal to hydraulic retention time. So, as soon as you recycle the cells, the mean cell residence time should be higher as compared to that hydraulic retention time. So, again we try to discuss the effectiveness, how the sludge settling property can be expressed with the help of sludge volume index. And now today I want to discuss two numerical problems on this particular activated sludge process. And first problem we will discuss the process design. And this process design, we can not only we know that most of the biochemical processes, they are aerobic fermentation process, and aerobic fermentation process major bottlenecks is the dissolved oxygen concentration. Because why? Because microorganism, they can utilize the oxygen which is dissolved in the fermentation media. So, and since oxygen is sparingly soluble in water, so that is the major limiting factor in the aerobic fermentation process. So, since activated sludge process is the aerobic fermentation process, we can extrapolate this process design for normal biochemical fermentation process also. And in the next lecture, I shall discuss the anaerobic fermentation process. So, we can also find out how we can design the anaerobic digester. So, let me start this today, that with the activated sludge process. Now, if you look at problem that we have here, this is, if you see that design of a continuous flow start tank activated sludge process to treat 0.25 cubic meter per second of settled wastewater. Settled wastewater, I try to discuss that when wastewater comes to the that suppose this is the activated sludge process, when it comes first is comes to the primary clarifier. Primary clarifier, the main purpose is to separate out the suspended particles, then it goes to the activated sludge process, then again it goes to the secondary clarifier, finally it goes out like this, and suspended solid we can separate out here. So, this is exactly what is mentioned, the design a continuous flow start tank activated sludge process to treat 0.25 cubic meter per second of settled wastewater having COD BOD 5 is 250 milligram per liter. Effluent has 20 milligram per liter of BOD 5 or less. Assume the temperature is 20 degrees centigrade, that the following conditions are applicable. The influent volatile suspended solid in the reactor is negligible. So, I told you the volatile suspended solid actually that indicate the presence of cell mass, because most of the cell mass, they are organic mass. So, here we can assume the x0 equal to 0, and mlVS by mlSS is 0.8. I explained in the last lecture. mlVSS means the organic that cell mass, and mlSS is the total suspended solid, and suspended solid comprises of both the organic and inorganic material. Inorganic material we consider as the inactive biomass. Now, XU is the settled cell mass concentration, but this is suspended solid. So, this is not exactly the cell mass concentration, but if you multiply it with 0.8, then we will get the settled cell mass concentration. And this is mlVS, that is the cell mass concentration X equal to 3500 milligram per liter. Theta C is the solid retention time or mean cell residence time, that is 10 days. Hydraulic system of the reactor is continuous flow start tank. This thing is very important because the effluent contains 22 milligram of biological solid, of which the 65% biodegradable. Now, I want to tell you here, suppose this is the activated sludge process and this is the CSTR, and here you have a starter and here you have the sedimentation tank. You recycle back to the reactor. The supernatant is this is actually the this is called influent, this is called influent, and this is called effluent. Am I right? So here x0 equal to 0, and here xc we also this tends to 0. This is also tends to 0. That is, we usually assume, because we assume that the very less amount of cell mass present. But here the problem is like this. They are saying that effluent content 22 milligram per liter of suspended biological solid. That means due to the inefficiency of the separator, some solid material cell mass may overflow and it comes with the effluent. Say 65%, the value of BOD5 can be obtained by multiplying BODU by 0.68. Waste contains adequate nitrogen, phosphorus and other trace nutrient for biological growth, and the specific death rate of the cell 0.06 day inverse and yield coefficient 0.5. 1 day sustained peak flow is to 2.5 times the ever flow rate. This is the problem that we have now. So what we shall have to do first, the process is like this, that this is the reactor, and we pass the Q is the flow rate, Q0 is the flow rate, and S0 is the initial substrate concentration, X0 is the initial cell mass concentration. It comes in the reactor, and under steady state condition the cell mass concentration is X and substrate concentration is S, and V is the volume of the reactor. Then it comes to the clarifier or separator, where we separate the cell mass, and this is the settled cell mass concentration is XU. It is recycled back to the reactor like this, and this is an effluent is coming out like this, and this is the wasting this flow rate of the sludge, and this is the settled. This is XR is given. This will be XU. We will be using the XU. This is wrongly given. So now let us see how we can solve this problem. Now here that what is the purpose of this activated sludge process? Purpose of the activated sludge process is to remove the soluble organics present in the wastewater. Now, how you can remove that? Your organism grow in the wastewater and convert the soluble organics to insoluble organics and carbon dioxide. Carbon dioxide will go out of the system and cell mass remain in the system, that we can easily separate it out. So, so actually that is due to the inefficiency of the clarifier, we cannot separate all the cell mass. So, some cell mass remain with the effluent. So, that is not the fault of the activated sludge process. Now, if you want to calculate the actual efficiency of the activated sludge process, we shall have to consider the BOD5 of the soluble organics, not the insoluble organics. So, the outgoing liquid has two parts, am I right? It has the soluble organics, soluble plus insoluble. So, we shall have to calculate what is the BOD5 of the soluble and BOD5 of the insoluble. Now, this is equal to the total BOD5 of the effluent, BOD5 of the effluent. Am I right? Now if you can find out BOD5 of the insoluble solid material, then if you deduct with total BOD5 of the effluent, then we can find out BOD5 of the soluble liquid. So, this is exactly what we are doing here. You see that the effluent BOD5 equal to BOD5 of the soluble effluent, BOD5 of the suspended solid. Now biodegradable portion of the effluent is we have 22 milligram per liter of the biological solids, of which the 65% is biodegradable. That means biodegradable organic matter is 14.3 milligram per liter. Now, we know that for the oxidation of 1 gram of biomass, we required 1.42 grams of oxygen. So, we can find out this much oxygen will be required for oxidation of the solid material, and then BOD5 of this material, if you multiply it with 0.65, because we have written in this problem BOD5 is equal to 0.68 into BOD U means that ultimate BOD, the total BOD that we have. So, we can easily find out the BOD 5 of the suspended solid. Then we can find out the BOD 5 of the soluble effluent is 20 minus 13.8, that is 6.2 milligram per liter. Now, when you when you talk about the process design of any kind of biological process or chemical process, first parameter we shall have to determine that what is the conversion efficiency of the process. Now, here we have seen that we have two type of conversion efficiency. One is overall plant efficiency and there is the biological efficiency of the process. Now, if you look at the biological conversion efficiency of the process, that will be that is the BOD of the soluble incoming liquid. Here is the 250 milligram per liter BOD 5 and here is 6.2 milligram per liter. This is we have found out this by biological conversion efficiency of the process will be 97.5%, but overall plant efficiency, if you consider, so it is 250 and here 20. So, that means 250 minus 20 by 250 is coming 92%. So, this is how we can calculate the plant efficiency. So, when you do any kind of process design, first parameter you shall have to monitor that what is the conversion efficiency of the process. Second parameter we shall have to find out what is the volume of the reactor. The volume of the reactor is like this, and in this I want to point out that these parameters, particularly y x by s, this 1 plus mu d plus theta c, this is considered as y x by s observed. Observe means this is the we know the suspended material. When we talk about the yield coefficient, what is the overall yield coefficient? Gram of cell mass produced per gram of substrate consumed. Now, this gram of cell mass, when you consider about overall yield coefficient, it comprises of two type of biomass. One is called viable cell, another we call dead cell. Now, when cell multiplies, only the viable cells will multiply, dead cell will not multiply. So, observed yield coefficient will be something else. The observed yield coefficient, we shall have to consider the date of the cells, and it will come as y x by s, y 1 plus mu d plus theta c equal to y x by s, this observed yield coefficient. Now, here this is the expression for the volume, and we in this problem we have all the parameters. You just put the parameters, we can easily find out the volume of the reactor. So, second part of the problem is that how to find out the volume of the reactor, am I right? So, now next is that what is the amount of solid produced per day from the reactor, that we shall have to find out. Let us see how we can find out. Then I told you the y observed equal to y by 1 plus mu d plus theta c. This is the observed yield coefficient, and this is coming. I can tell you actually that we overall this overall yield coefficient was how much? This was 5. But when you consider calculate the observed, that is coming, so it is much less than the overall yield coefficient, because it comprises of both the dead cell and viable cells, and it consists of mostly the viable cells. So, we can so this is what is this parameter? This parameter indicate Q0 into S0 minus S indicate how much BOD that is removed. So, if we multiply it by this factor y observed, we will easily get the how much cell mass is produced. This is the cell mass is produced. Now, once we know the how much cell mass is produced, this is the volatile suspended solid. Now, if you divide by 0.8, then we will get the mixed liquor suspended solid, that is the sludge. So, this is what we can calculate how much sludge is producing per day. Next is that volumetric, the sludge wasting flow rate. Now, how you can find out? I told you that in this reactor, this is like this. This is coming in, and a part you are going out, and part you are recycling back. Now, here you have QW, XU, and S. Am I right? And here you have what? QW plus QR, and QR is the recycle flow rate. And here is the cell mass concentration. Now, what is the theta c is the solid retention time. How you can write this is B is the volume of the reactor, X is the cell mass, X B into X divided by QW into XU. XU, that is the how much rate of cell mass wasting from the reactor, and this is the how much cell present in the reactor. So that gives you the what is the solid retention time. Now, if in this equation we can easily find out QW. QW is the volumetric sludge wasting rate. If you put all this value, we will get 205.7 cubic meter per day. Now, next is that what is the recirculation ratio, that we can easily find out. Recirculation ratio we can find out that this equation, that recirculation ratio usually we find out by alpha. This is alpha is equal to Q ward by Q0. This is the recirculation ratio. This is, I think there is some mistake, we can make the correction. Then this we can find out through the material balance across the reactor. We can easily find out that then we can find out that what will be the value of Q ward by Q0. Now, hydraulic retention time, that is hydraulic retention time theta can be easily find out V by Q0, that is you can easily find out. Then V we know, then Q0 you can know, so we can find out the hydraulic retention time. Now, oxygen requirement we can easily calculate. How you can calculate the Q into S0 minus S, that is the amount of BOD that is removed, and then this is this is the BOD 5 and 0.68. If you divide, then we will get the total BOD that should be removed. Now, when your wastewater this much of BOD is removed, a part is converting into cell mass that remain in the reactor. So, the BOD equivalent to cell mass that is to be deducted, and BOD equivalent to this is the amount of cell mass that is produced, and this is 1.42 is the conversion factor. For the oxidation of 1 gram of the cell, you required 1.42 gram of oxygen. So, if you divide, we can find out the figure that what is the exact amount of oxygen that is required in this particular process. Now, the F by M ratio, that also you can easily calculate what is the F by M ratio. F by M ratio is the food and microorganism ratio. What is the food? Total food is the Q0 into S0, and what is the microorganism present in the reactor? V into X. So, we can find here, because F by Q0 is the 1 by theta. So, this is replaced by theta. Theta is the hydraulic retention time. So, you can easily find out what is the F by V ratio. And then volumetric loading, that we can calculate by this that per unit volume how much BOD is loading, that we can per unit time, that we can calculate from this. Now, how you calculate the amount of air requirement, that is very important, because previously we have already find out how much oxygen is required. This is the amount of oxygen required. Now, air content 23.2% of oxygen. So, if you divide by 0.232, you will get the amount of air that is required. Now, air has the density of 1.2021 kg per cubic meter. So, you will get the volume of air that is required for this particular process. Now, all oxygen present in the air, all oxygen cannot be transferred into the liquid. So, there is some kind of oxygen transfer efficiency, that is we consider about 8%. So, if you divide by 0.08, we will get the exact amount of oxygen, that is air that is required for this particular process. And for designing purpose, always we consider some kind of factor of safety. Here we can consider 2 as the factor of safety. We can find out that what should be the air requirement as about 336 cubic meter per minute. And here we can say air requirement per unit volume of the effluent. This is the amount of effluent is to be treated, this is the amount of air is required. So, we can find out cubic meter per cubic meter of that effluent that we can calculate. The air requirement per kg of BOD removal, that also we can calculate with very easily. So, if you know that this is the amount of air requirement and this is the amount of that BOD that is to be removed, and then we can find out for the per kg of BOD removal how much air is required. So, this is considered as the process design. The process design basically we mean that for running for operation of the process, whatever parameters we shall have to monitor, that is to be estimated, that is called process design. Now, second problem also very interesting. If you look at that, one step aeration activated sludge process is to be analyzed as a series of continuous flow start tank reactor. Now, this is the four tanks. This is 1, 2, 3, 4. Fourth is the activated sludge process. They are continuous start tank reactor. They are attached with each other in series. Now, then this is the clarifier. This is the clarifier where you separate out the cells, and if cell you recycle back to the system. Now, if you look at the flow diagram, these cells it comes in contact with the flow stream, that is the feed. This is the feed or wastewater that is coming in. So, they are mixing together and then they are equally distributed in the 4 different reactor. Am I right? You can see that this is distributed like this. So, then here the liquid is coming, and then after the concentration is continuously operation, then the liquid is entering into second reactor, and here is coming, and then this is. Now, here I want to point out one thing, that if you look at the flow rate of the what flow rate the incoming liquid coming in the first reactor, that is F. Am I right? Now, in case of second reactor, we have 2 flow rate, here F and here F. So, overall flow rate is 2F. So, here you have 2F. Am I right? So, this in the third reactor, this what is the flow rate? 2F plus F, that is 3F. So, here it is coming 3F. Am I right? It is 3F is entering, and fourth reactor will be 3F plus 4F, that is 4F. So, this is the overall flow rate in the fourth reactor. So, this is how, let me see how we can solve this problem. And I told you that whenever you want to solve the problem, you try to write down all the operational parameters that we have. You can write it down. And now, let us see how we can find out the overall flow rate of individual tank. So, F0 is the incoming flow rate. Am I right? This is F0 and this is F hard. This is here F0 and F hard, and then it is divided into 4 different reactors like this, equally it divided like this. Am I right? So, basically it is F0 by F hard divided by 4. So, the flow rate of individual reactor here, it will be 300 cubic meter per day. Now, question comes, what is the value of S? Now, here the S0 value is the substrate concentration is 0, and here substrate concentration is S. Am I right? Now, S4, because it is coming from the fourth reactor. So, we can write F0 into S0 plus Fr into S4 divided by 4F, then we will get this value, that means 170 milligram per liter. So, S value we can find out. Similarly, we can find out the value of X also, what is coming in here X, here X, here X, all this X value you can kind of F0 into X0, this is X0, and here this is XU. Am I right? So, Fr into XU divided by 4F, you calculate 3.3 grams per liter, that we will be getting. Now, when we do the substrate balance in the first reactor, then how we can write the substrate balance is the rate of input of the substrate, rate of generation of substrate, output, consumption and accumulation. Now, this will be equal to 0 in case of substrate, and rate under steady state condition accumulation will be 0. So, we can write F into S, F into S1 ds by dt into F. Now, ds by dt we can write in this form. So, this we can write in this form, the F into S minus S1 y x by S by V equal mu z into x1. Now, if you write the cell mass balance, also we can come across this equation. So, this what is the net growth of the cells is mu z into mu d. The mu z is the growth of the cell, mu d is the death of the cells into x1. This is equal to this. Now, this equation we can write in this form. This is and then from equation 1 and 2, if you look at this equation, we have written in this form the mu g into x1, and this equation also we find out the expression for mu g. So, the 1 or 2 that one side is the same. So, we can equilibrate the equation, we will come across this equation. And then this equation you can write to find out the value of x1, and where our equation will come, and x1 will be equal to that f by v is equal to what? 1 by theta, because we know theta is the hydraulic detention time, is equal to v by f. Am I right? So, this we can write in this form, y by x, this is f by v I can take common, and this also we can take common, and we can have 1 plus mu d into theta. Now, then from this we can write a generalized equation that x n equal to S I in minus S n y x by s plus x I divided by y 1 plus mu d plus theta n. Now, what do you mean by theta n? Theta n is the hydraulic detention time of the in tank, x I is the cell mass concentration of the incoming liquid, x n is the substrate concentration leaving the nth tank, and S I is the substrate concentration of the incoming liquid. X n is the cell mass concentration of the nth reactor. So, what we can do that after writing this generalized equation, now we can consider the first reactor. In the first reactor, what we can write, that x1 equal to this S will be that S, that the reactor, that S is coming this with the mainstream, the S minus S1 is going out like from this is the number 1 reactor. I can write that this is x. X is here is the value of x, that is the incoming liquid, and 1 plus theta into mu d into theta. So, if you put all these values, we can find out the cell mass concentration here is like this. Now, similarly, we can find out the SI value and XI value and X2 value, that we can find out in the second reactor. How we can find out in the second reactor, that in the second reactor, if you consider in the second reactor, suppose this is the mainstream and this is the first reactor, this is the second reactor, and this is coming like this. So, here there is the F is the flow rate, this is F is the flow rate, this is S1, this is S. Am I right? So, we can write the SI, the incoming substrate concentration, the F into S plus F into S1 divided by 2F will give you 87 milligram per liter. Similarly, Xi also we can calculate, we will find this. Now, theta 2, the hydraulic detention level, this is the volume of the reactant, the total flow rate is F plus F is 2F. So, we can find out 0.4. So, if you put this value in the equation, we can get the value of X2. Now, similarly, I can solve the reactor 3 and reactor 4. Similarly, it's the same solution we can get, and so what in conclusion, what I want to tell that in the it is very easy to do the process design of activated sludge process. We can find out, first we shall have to find out the conversion efficiency of the process, and then we shall have to find out the volume of the reactor, then we can find out how much sludge is producing per unit time. Then we can calculate that what is the hydraulic retention time, what is the solid retention time, what is the flow rate or wasting flow rate of the sludge. Then we can find out the exact amount of air that is required for this particular activated sludge process. And I try to solve some kind of step aeration process just to find out that how to the cell concentration in after different reactors when they are connected in series. Thank you very much.